think we should start up again. And we'll continue this series of the first two lectures on what we're calling gravitational wave basics. I think Johan did a great job of giving us some intuition for, how the amplitude and frequency of gravitational waves scale, and that binaries generate them, and how strong this strain is. What I'm going to talk about is a continuation of that, and in some ways, some of the same concepts, but we're going to get at them in a little different way and hopefully gain some even more insight. And to start, I want to flash this plot again, which you might guess I like a lot, even though maybe it doesn't look very informative at first if you're not familiar with it. But what I'm going to try to do throughout this lecture is explain how to make this plot. And then hopefully we get an idea more of what this plot means. But just again, quickly, the y-axis is this strain. It's actually a specific version of the strain called the characteristic strain, giving you some information about the amplitude of your gravitational wave. And the x-axis spans these, 12 to 14 orders of magnitude in gravitational wave frequency, along which we find these very different sources, which these sources of merging black holes, compact objects, are drawn in here in these colored lines that are kind of, shooting higher in frequency towards merger. And also plotted on here, these gray and black bucket-shaped curves are the different sensitivities of different detectors, which throughout the week we'll talk about because different detectors are good at looking for different types of merging binaries. So we'll get more to this throughout the week, and we'll get more, as I said, to the different sources of gravitational waves. But to back up, what I want to go over are some really just fundamentals and how we get there. So throughout this lecture, what I hope we get to is fundamentals of gravitational wave propagation and production. Then we'll get to this idea of why changing quadrupole moments generate gravitational waves by deriving the quadrupole formula. And I hope at the end we look at a little overview of the different types of emitting compact object binary merging sources. And then hopefully you have everything you need to make most of that plot and understand why that plot is useful. So let's start from really the beginning. It's a gravitational wave, right? So where does the wave nature of the gravitational wave come from? Well, the first place to start is here, Einstein's field equations, right? Where the left-hand side, in terms of this big R, the Ricci curvature tensor, is a function of the metric and derivatives of the metric, and tells you about the curvature of space. And the right-hand side tells you something, right, about the stress energy, the matter energy in that space, and how those two are related to each other. And so, unfortunately, this isn't a review on GR, but we're going to start here with the results of GR, general relativity, and ask how do gravitational waves come out of this theory and these field equations. Well, the easiest thing to do first is to simplify this and say that the right-hand side is 0 and work in a vacuum, essentially. And the idea behind that is we want to know something about these propagating disturbances, these waves. And so you can say when you're far away, you're agnostic of the source that's creating gravitational waves. How do they propagate? How do perturbations propagate? And so we start with the vacuum field equations, which are a lot easier to deal with at first because they simplify to this Ricci tensor equal to its components equal to 0. And then I'm just outlining this derivation. You say that we want to assume that these perturbations, these waves, are just really small perturbations, which we call H. It's a second order tensor H. And those perturbations are small, and they propagate on some flat background, which here we just call eta. So this is flat space, Minkowski space. And our total metric is just flat space with these perturbations moving on top of it. And we want to plug this into the vacuum field equations and solve for H. What do the perturbations look like? And we're calling it H for a good reason. As we know from the first lecture, this will end up being our strain. So this simplifies. If you plug in this metric with this small h, and you keep all the terms that are linear in h, this is the linearized field equations, linearized vacuum field equations, you get something that might look familiar. This is a wave equation for the components of our metric perturbation h. So this is just, again, a very quick sketch of starting from Einstein's field equations, how you can ask, how do perturbations far from some source propagate, well, they propagate following a wave equation. And if you write down this an example solution to that wave equation, which I've written here in a suggestive coordinate system, then you see here that our components are all, so here I've chosen them to be moving in some z direction, arbitrary z direction at some frequency f. And so they're oscillating plane waves, but here with these, only these non-zero metric components. And what you get from this solution, what you can gauge from this solution, is that gravitational waves, yes, they're waves. They have two different polarization states, which I've suggested by writing these different components here, H plus and H cross. And they're transverse. So this is a wave moving in the z direction, but it only has x and y components in the middle. So they're transverse waves with two polarizations. Quick question? Yeah, so I think that's a good question. You'd have to, you're free to, with a choice of gauge here, just like in electromagnetism, you can choose the Lorentz gauge. And when you do that, you get rid of certain components of the metric tensor you're allowed to. And you can write it this way in this transverse traceless gauge. So there might be a deeper answer to that if you go through it, but that's essentially it. There's a gauge freedom. Oh, sorry, thank you very much. The question was, why are there no zero components in this metric tensor? Why is it all spatial? Oh, oh, okay, sorry. Maybe Jonah has a better answer. I see. So another point to be made that this is the linearized equations. When you go to higher order, which we'll mention briefly, because you need to go to higher order to understand the energy in a wave, then there are other components. Thanks. So from this, though, we can get a better feeling of what these polarization states are and what does a passing gravitational wave do? How do we detect it? Just from these linearized solutions for the strain, the metric perturbation. So if we take this solution and we say, maybe you've seen a picture like this before, we have some freely falling test particles, all these black dots, arranged in a circle in flat space, and that circle has diameter L. Then we can ask, carry out this kind of illuminating calculation, what's the proper distance between any 2 points over time with our metric solution, this G sub mu nu. So this is just the definition for proper distance. And we can carry this out with our metric that we just solved for over here on the right. So if we plug in this metric to this proper distance, and we keep, again, kind of first order terms in H, you can try a few examples that are illuminating. The first example would be, let's say we only have this plus polarization, only these plus components here. And let's compute this proper distance only in the x direction. And what you can come down to is that you find that this distance as a function of time is simply the flat space distance in the x direction plus this extra oscillating term, proportional to the h plus this kind of amplitude of our metric perturbation. And if you, so you should try this later. If you can do the same thing by saying that we only want to measure this distance in the y direction, and you find another similar oscillation, but in the opposite direction. So you can imagine what that will look like, but I can show you a movie as well. And I'll get to this in a moment. If we look at this movie now, where this, if we were to compute that proper distance between all those points in all the directions, not just x and y direction, then you'll see something, if we plot their positions, their distances over time, their separations over time, you'll see something you might have seen before, these kind of two different polarization states. Well, here we have this plus polarization state. And here, if we were to do the exercise again, but only look at the cross H terms, we get the same kind of oscillation, but rotated at 45 degrees. So this is kind of the meaning about what our solutions mean as they pass through these freely falling test particles. This is what a passing gravitational wave does. And you can show this not only by calculating this proper distance, but If you study general relativity, there's something called the geodesic deviation equation, which just tells you what is the separation vector between freely falling points over time. If you solve that, you get the same result. So that's, again, just from these linearized vacuum field equations, you get this idea of what the strain is. And as Johan wrote it before, you write it as this delta L, this change in distance over the original L. And you can see you can get that from rearranging these equations here for H. And so you would define H this way, and that's why it's often called the strain in analogy to mechanics. It's kind of a fractional change in separation. Okay, so that gives us some idea of what the gravitational wave passing does. And this is, of course, how the very basics of how they're detected. Jonah and Alberto later are going to talk more about this, right? Because these freely falling masses are, for example, mirrors in this interferometer. And as their distances change, this is how LIGO works. I'm not going to talk too much about this, but I'm just going to flash the video here for foreshadowing for later to talk when we talk about how detectors actually detect these passing gravitational waves. And of course, this is LIGO. I'm just going to shoot through these. This is LISA will work in the same principle, but in space with longer arms. And then there's also these pulsar timing arrays, which are really exciting and will be talked about on Thursday. But rather than using interferometer, these have test masses they're tracking the distance to. But these test masses are clocks in space, are pulsars that are distributed throughout the galaxy. So the point is all these detectors work on the same principle. Passing gravitational wave changes distances between freely falling particles, and we can track that some way or another. Okay, back to equations for now. So Johan, again, gave us this quadrupole formula from dimensional analysis. But you can also get it from the Einstein equations. And so now we can say we actually care about what generates the gravitational waves. So we add back in the matter, the stress energy that is creating gravitational waves into the Einstein equations, and we try and solve this equation the same way that we did in the vacuum case. So we again assume there's some small perturbation of flat space, which is our gravitational wave. And we linearize these equations. I'm just going to put some details to this derivation if you want to try and follow it later. But you just redefine your variable and you choose a gauge condition. And you can, again, write the Einstein field equations to linear order in a way that looks like a wave equation for the metric, for the perturbation to the metric. But now it's a sourced wave equation because we left in the right-hand side the stress energy, T mu nu. And you can solve this equation with standard techniques, green functions. Okay. And to do that, you do one kind of illuminating thing. So you do this Green's function technique, but you also use a few tricks. One is that you use energy conservation in flat space because we're to linear order. And so this is expressed here. It's okay if you're unfamiliar with this, writing it this way, but this is essentially stress energy conservation. And we use that plus the gauge to simplify this. And well, some integration by parts too. And when you carry out this calculation, you arrive at what is called the quadrupole formula, which is the kind of famous quadrupole formula that Johan was mentioning and derived dimensionlessly. But this is how you would do it from Einstein's equations. And it's kind of interesting because Johan talked about conservation of mass and momentum tell you that the kind of first order contribution of gravitational waves should be quadrupole. And that's a completely valid and very conceptual argument, but you see how it comes out when you do this because you have to use these conservation equations. And in the end, these conservation equations using these relations is what brings you from this wave equation and Green's function solution down to having first order quadrupole moment terms in your formula for the strain. So right, this is our metric perturbation, and this is the second derivative of a quadrupole moment. And here, you just have this definition of the quadrupole moment. So this T00 term is essentially just the mass density of whatever our source of gravitational waves is. And these are just moments of position. So Johan wrote mr squared for a binary. That's why it's coming out to be roughly mr squared. Okay, and that's something you should try if you haven't. Maybe some of you have already done it, but that's a classic derivation of the quadrupole moment. Okay, and to do this though, we assumed that our source was non-relativistic. We assumed a number of different things, but that's the main one. You can do the same thing in electromagnetism to get the dipole moment formula. So we assumed, right, that our source is made up of all these components and they're not moving relativistically, and we're very far from the source for this to be accurate. Okay, so that was our quadrupole formula. And I just wanted to make one point here. We can just look at this quickly. You notice there is no angular dependence on the strain in that expression. But if you project, and I'm just going to give the ingredients here, project that solution onto, for example, an observer at some direction with unit vector n, then what you find, this is again just the ingredients to this kind of projection you can find in the textbook, you find that your quadrupole formula is a bit altered. And it has this normal part before the second derivative of the quadrupole moment, but also these other pieces, which are directional pieces, which tell you that there is some pattern to the emission, right? So it's stronger viewing from some directions than other directions. And more than that, the polarization, the components of the polarization that you see are mixed differently depending on what angle you're viewing this source from. And so that will depend on the quadrupole of the source, and it'll depend on the viewing angle. So if you do this for a binary, which we'll do in a moment, you can find some standard expressions for what components of the polarization and what amplitude of strain you see, depending on whether you're looking at the binary edge on or face on. And so these are kind of standard expressions you can find in textbooks, but the idea is here. You have this quadrupole moment and you project it to some observer. So I just wanted to mention that because that is an important piece that comes up every now and then. Okay, so we're back to this solution, and I wanted to now do the classic example like Johan did for a binary. So we have this binary. It has two masses, m1 and m2. And it's often really convenient to write this reduced mass, mu, which is just defined this way. And our binary is orbiting at some angular frequency omega, and it's separated by some separation big R. And you can go through this. It's a nice calculation to do where you write down this version of our quadrupole moment tensor, and you just prescribe a path and orbit for your binary. So we're just going to say we're not going to use the laws of gravity. Well, we're going to use Newtonian mechanics, the simplest kind of Newtonian orbit of a binary in a circular orbit, and write down a parameterization of its path here. So this is just the x and y components of a binary in the xy plane orbiting at this angular frequency. And if we then plug these into the quadrupole moment tensor and take the second derivatives, right, you should get to this expression. And one more step, we choose some observing direction. A very simple one is we're just looking above or from below. And you get this expression for the strain from a binary as observed from this direction. And so what I want to look at now is what we actually found by doing this, because we have some amplitude and we have these oscillating components of the different components of our metric. So what does it look like? Well, the amplitude is what you would have guessed based on the dimensional analysis. If you rearrange these terms, remember this mu is like a mass, then you get something that looks like a gravitational length over the distance. So the distance in units of gravitational length times the orbital velocity in units of c. So as before, you see that this strain falls off as 1 over d in units of gravitational radii, and it's larger for higher orbital velocities. So for kind of the most extreme thing you could think of, two black holes merging, say 100 solar mass black hole at 100 megaparsecs away, you can plug in some numbers. You see, as Johan said, this number is tiny, and that's why the strain is tiny. But the biggest you can usually make this is about 0.5. And so you can get these strains of order 10 to the minus 20 for these bigger black hole systems. Well, 100 solar mass black holes. Okay, so that's the amplitude out here within a factor of a few, depending on what components of the polarization you have. The other important thing to notice is maybe you've heard many times that gravitational wave frequency from a binary in a circular orbit is just twice the binary orbital frequency. And that you can see come out very clearly here. This wave is oscillating at twice the angular frequency of the binary's orbit. And just to get a good feel then for what that is, you can write from the two-body problem, just a Newtonian two-body problem, what the orbital frequency is, take twice that. And you can see that, again, for about 100 solar mass black holes, you're talking hundreds of hertz near merger. And so again, this is the kind of regime LIGO is in the hundreds to 1,000 hertz. Oh, so that is just a guess I took, because if you take a test particle orbiting a short-shield black hole, at the innermost stable circular orbit, its orbital velocity is 0.5 c. So that's just a kind of rough guess for that. It can be a little larger for spinning black holes. And of course, yeah, so that's where that's from. Yes, I always forget. Now that's your job to remind me. The question is, why choose V orb 0.5 c as an upper limit? And the answer was, that's the innermost stable circular orbital velocity for a test particle around a short shield black hole. Okay, so we've gone through the quadrupole formula for a binary. And I just wanted to rearrange this amplitude, because I often think of this in different scalings. And so here we have it in terms of the orbital frequency and the separation of the two black holes and the reduced mass mu. But we can use the two-body problem again to rewrite this. And so I'm going to rewrite it in terms of mass and frequency, because as we were seeing before, Johan was talking about how we can recover these types of binary mass, for example. And I'm going to do one more thing. I'm going to again define the gravitational wave frequency in terms of the binary orbital frequency. And I'm going to find this script m called the chirp mass, which you might have heard of. And it's this strange combination of the reduced mass and the total mass of the binary. But when you plug those in, this simplifies nicely, or I don't know if you would say that actually, because I actually have another c to the fourth here. You can forget that. But what it does give you is that it scales with the chirp mass to the 5/3 and the gravitational wave frequency to the 2/3 over the distance. And so this is just a convenient form that I use often if you want to talk about sources that have some mass, some chirp mass, and you have a measurable gravitational wave frequency. And we'll probably get back to that in a moment. But okay, so you can do that. I just wanted to show that for now. But let's get back to, so this formula for the strain is at a fixed gravitational wave frequency. It's for a binary that sits there forever and orbits at this gravitational wave frequency with this fixed mass, chirp mass. But as Johan told us, gravitational waves carry away energy and angular momentum. And you can write down the stress energy tensor to first order, actually it's the second order in this metric perturbation, of how much energy momentum a gravitational wave carries. And so we're not going to do that, but it's essentially, as we mentioned earlier, it's expanding not only the linearized equations, but to the second order. And when you do that, you can collect terms that tell you how much energy the gravitational wave is carrying. And this is summarized in what's called this Isaacson formula. The point is, you can use this stress energy to ask how much energy, how much energy is the gravitational wave carrying over some sphere at infinity. And you can derive another version of what's sometimes called the quadrupole formula for the luminosity of gravitational waves that are carried away. So this E dot, this change in energy over time due to the gravitational waves being emitted, is again proportional to this 1 over the Planck luminosity times these third derivatives of your quadrupole moment. So that's a great question. To do this calculation, you have to average over a few different wavelengths of your gravitational wave, and this has something to do with the non-locality of energy in general relativity. But this is an average over a few wavelengths of your gravitational wave. Okay, so we're getting to, so this is just again a really rough idea of where this comes from. You'll see this expression a lot, and it's very easy to use. This is roughly where it comes from, the energy carried in a gravitational wave. You can go through the exercise we did and use that quadrupole moment for the binary, but take its third derivative now and carry out this contraction, and you get the energy carried away for a binary in terms, again, of this chirp mass, and I still have the orbital angular frequency here. And so we go back to what Johan was talking about with luminosity. We can rewrite this, again, with our two-body problem, right? This is just the binary separation in terms of total mass and orbital frequency. And you can write it this way. And so we can go back to Johan's exercise and ask, what is this maximum luminosity of gravitational waves? And if we plug in for R, again, of order a short shield radius or just a gravitational radius, then you can immediately see that these M's cancel out. Remember, there's an M here, so there's 5 M's, 5 M's. and you get something that's proportional to the Planck luminosity. So when black holes merge, you're always getting something that's approaching the Planck luminosity. There are, of course, corrections when you add in general relativistic effects at the very end. This is not valid there, but this is, again, where this idea of this Planck luminosity comes from. And if you plug in numbers, maybe you've already did, it's something like 10 to the 59 ergs per second, which is almost a ridiculous number. I'm not sure how to tell you what that means, right? Like let's see, so quasar emission, accretion, Eddington luminosity of a 10 to the 10 solar mass black hole is 10 to the 48 ergs per second. The brightness of a galaxy is like 10 to the 40, 10 to the 51. So a supernova or a gamma ray burst is 51, 52, right? This is 100 million times brighter than that. So that's why people say mergers of black holes are the brightest things in the universe, because they are. All right. So we're marching along here. What time do we have? Okay. Right. So from that, we can derive the frequency evolution, because we had our strain in terms of a fixed frequency, but we want to derive the frequency evolution. Again, to do that, we go back to the two-body problem, and we can essentially write the orbital frequency in terms of the orbital energy. This is just the two-body problem. And once you do that, you can take a time derivative to relate the time derivative of your binary orbital frequency to the time derivative of the energy that's being carried away. This formula here for the gravitational waves. And when you plug that in and rearrange, you get this expression that Johan had from dimensional analysis, again, for the gravitational wave change, chirp, over time from a binary, with these 5/3 and 11/3 everywhere, but that's what comes out. And we've been using this script m, which I've called the chirp mass. And if we look at that formula for the gravitational wave change decay rate over time, the frequency, the change in the frequency over time, here, you can see why this is called the chirp mass, because you can rearrange for this m, this chirp mass, which is again a combination of m1, m2, m total. And you can write it only in terms of the frequency and the frequency derivative. So it's called the chirp mass because you can measure this chirp, this increase in frequency over time, and the frequency at any time, and derive this quantity, the chirp mass. Right, and this is, maybe you've seen many times, this chirping. Right, that frequency derivative and frequency can give you an estimate of the mass, or the chirp mass. And I wanted to rearrange this one more time. You can plug that in and write the strain then, just in terms of a distance, the frequency and the frequency derivative. And this is really what so I think this is interesting because you can, maybe we'll get to this later, but Johan was mentioning you can measure a distance from gravitational waves. So you can do that by measuring the strain, the amplitude of the wave from our detectors, and measuring this f dot and this f. Those are the observables you get. And in an expanding universe, these are redshifted. So the redshift also comes in here, and this builds into how you measure luminosity distances and the standard sirens approach to measure the Hubble constant. Okay, so that's a picture for the strain, the evolving strain from a binary, from Einstein's equations to here. Is it possible to get the redshift information from gravitational waves? It's usually done with electromagnetic observations, but so I wrote a paper on it last year, so not to advertise that, but there are some ways you can do that. And it involves either knowing something about your source, so you know the mass or something a priori, or it involves having very big detectors where you can measure a different kind of distance, a parallax distance across your detector. And you can only do that with pulsar timing arrays. So yeah, so exactly. With pulsar timing arrays, if you're lucky, you could measure a black hole merger and only from gravitational waves measure two types of distance. One, this type of luminosity distance, and two, a parallax distance, because your pulsars are kiloparsecs away and you can parallax. Yeah, we could talk about it later. Yeah, you can estimate how far away you could do this for. And yeah, so Yeah, we could talk about that later. Yeah, great. Okay, so I wanted to finally get to that plot that I started with in the last 10 minutes here. So this is what we derived for the strain. And if you assume then that the frequency is increasing over time that we just saw it should, then you would at first wonder what's happening here. So for example, these purple lines are supermassive black hole binaries that are, it's their strain as they're evolving over time and they're getting closer and closer and their frequency is going up. And this is what their strain, we'll get to what C means, is evolving over time. So you would ask, this doesn't make sense because it looks like this H, this amplitude should increase with frequency as they get closer and closer. So what's going on here? The whole point of this comparison is to show that this characteristic strain is not the same strain that we've been talking about this whole time. It's a different type of strain that builds in this idea of detectability. Because you can estimate the energy in your total signal is not just the strain at some time, but it's the strain times the kind of the number of cycles that you accumulate. You see this oscillation for many cycles, you'll get a higher signal. So you can define this quantity, the characteristic strain, which is just our strain we've been looking at, times the square root of the number of wave cycles in a given frequency band. So you have some frequency resolution of your detector. How many cycles do you accumulate at that frequency? And that kind of enhancement gives you this idea of the characteristic strain. But what is number of cycles? Well, there's two regimes. One is that the binary doesn't really evolve much. Its frequency doesn't evolve much, so it's sitting at the same frequency. Then you're limited by your observation time. So the evolution time, chirp time here, the frequency you start at over the frequency evolution derivative, when that's much longer than the time you're watching for, the number of cycles is just the frequency you're at times the time you watch. So the other limit is that your binary is evolving very quickly. And so your observation time is a lot longer than the time it takes the binary to chirp, evolve through the frequency band that you're observing in. And then you can define this other number of cycles, just f times a different t, and this is this t, the time for the binary to evolve of order its beginning frequency. So if we use these two definitions of number of cycles and plug them into our characteristic strain, we get two different expressions. In the observation time limited regime, the characteristic strain still increases with frequency to this order. You can see that just by multiplying a root f by this 2/3. But in the chirp limited regime, we get this f to the -1/6. So these decreasing characteristic strain versus frequency are occurring because, yes, the strain is intrinsically higher, but we're seeing it for fewer cycles at higher frequencies because it's evolving much more quickly. So it's chirping very quickly through the frequency band. And so actually over time, as the binary black hole gets closer and closer, this characteristic strain decreases until it merges here at these little merger points. And so this is a useful quantity, and it's useful to draw on these plots because it's the quantity that shows up when you compute signal to noises, signal to noise ratios. So for example, this black curve is kind of the noise, the sensitivity curve for Lisa, right? So this is some kind of characteristic noise. And if you compute this characteristic strain as we just laid out, then this ratio of our characteristic strain curve to this black curve gives you an idea of the signal to noise you would expect for these systems. So this gives you an idea of detectability. If we were to have drawn this H, it'd be a lot harder to gauge by eye what we're looking at. So you often see these plots with these decreasing kind of strain versus frequency. And that's what it is. This is this characteristic frequency, which gives you an idea of what your signal to noise will be. And here, right, we've just drawn supermassive black hole binaries up here and more stellar mass compact object binaries that emerge in the LIGO band. Okay, so with the time left, I wanted just to give an idea of the range of frequencies that you expect for different sources, but I think we'll just go quickly through this. And I just wanted to show a quick plot. This was when you're in this observer time limited regime here at low frequencies, then you get this characteristic strain increasing with frequency to the 7/6, and that's just because you have to wait longer and longer and longer to get enough cycles to get a good signal. But let me just skip ahead and say you can find two frequencies quickly. One is this frequency where these two regimes meet each other. And that's kind of this knee, this peak characteristic strain you get for a binary. It's kind of the lowest frequency you might expect to see a chirping binary at, given its mass and the observation time tau. And so for these 100 solar mass black holes, this is actually around 10 to the minus 2 hertz. And I'll show that on the plot in a moment. And then the highest frequency is, this is really pushing the limits, saying that at a short shield separation of the two black holes, what is twice their orbital frequency? That's around 100 hertz, again in the LIGO band. So these final slides, I just wanted to show these numbers for a few different regimes. For these 100 solar mass black holes, like I said, you're going from, at the high end, hundreds of hertz. But interestingly, at the low end, you kind of enter into the Lisa band. And so earlier in the lives of these systems, they can be detectable in the Lisa band. And Alberto will talk about that some on Thursday. And these are the kind of astrophysical questions related to these systems. How do they form astrophysically? And there will be a lot of talk about that tomorrow. In the middle, if we go to lower frequencies, these 10 to the 6 solar mass black holes kind of range in frequency from, as you might have guessed, because Lisa was designed for this, these 10 to the minus 5 hertz starting points down to mergers at 10 to the minus 2 to 10 to the minus 1 hertz. And then finally, the last point of all of this, if you do the same exercise for this really massive 10 to the 9 solar mass binary black holes, then this low frequency, where above which they chirp, is actually higher than the pulsar timing band. So what that means is that these really massive guys aren't chirping over here. They're continuous kind of sinusoidal sources because they're big enough we can detect them before they're fastly chirping. So they're kind of sitting there forever. So if we detect single merging supermassive black hole binaries at these frequencies, we'll be able to see them forever. Well, yeah. Yeah, so for example, you can estimate that we would be able to see some evidence of chirp, measure the chirp, if we could wait for thousands of years. But what that means is that the pulsars in that array are thousands of light years away. So if we can detect a signal of them shaking and us shaking, then you can recover this chirp. But the merger time is, well, it's probably tens of millions of years, something like that. I don't know exactly offhand, but it's a very long time. But that's why these pulsar timing arrays are detecting a kind of a different type of thing. And really, what Steve Taylor will talk about on Thursday, it's not only looking for these single sources, but a so-called stochastic background of all these sources jumbled together. But I think I should end, and I'll end by just leaving up this. I gave you some of the information you needed to make this plot, and it might be fun to go see what you can do to make this type of plot with I just have some information here on where to grab a LIGO sensitivity curve. Maybe Jonah has better info where you can generate at least a sensitivity curve. And then you can add some bells and whistles to this by adding eccentric sources or adding higher order approximations to the strain with ring down and merger templates. So that's all for now. We can talk about this, of course, more throughout the rest of the week. I hope that's a good beginning for what's to come. So thanks. Yeah. Yeah. Yeah, that's a great question. So at the level I just presented, you'll notice, and of course, we just put the binary on a circular orbit and treated these as test masses. But that orbit will change when you add general relativistic corrections, including spin coupling, including eccentricity. So the actual orbit that it's on will be changed by general relativity. And as you noted, the orbit that we put in sets what the quadrupole tensor is, and that sets what our waveform is. So if you have different orbits that are affected by spins and these things, those orbits, those different orbits will show up in different waveforms. And so if you can compute what the waveform should look like at these high order, then you should be able to back out from observation of these waveforms what the spins and the black hole mass components and eccentricity are. So roundabout way saying spins, eccentricity, change the waveform. So we'll observe a different waveform. I don't know if you have another thought on that, Joe. There are some very complicated semi-analytic models for what the waveforms look like when you have spin coupling and these things, effective one-body problem, and a number of other approaches. So these are out there with many pages of correction terms. Yeah. Yeah. Right. So Jonah's giving a good example. This chi-effective, this effective projected spin does come in after this and affects the chirp in a way that you can measure and then say this is what chi-effective is. Yeah. Great point. Oh, so people are chatting in Zoom. I see. Yeah. And the question was, yeah, how do higher order, how do spins enter into the waveform so that we can extract spins from gravitational wave measurements? Okay, well, of course, yeah, Lauren.
I'm curious about those little gold stars.
Oh, yeah.
Are those like specific quasars or something like that?
No, that's a great question. They're in some way related to this little dash bump. These are white dwarf binaries in the galaxy.
No, actually,
Oh,
the ones
gold
in the
stars.
NBIA.
Oh, yeah. No, they're just my idea of asking what if there was a 10 to the 9 solar mass black hole in some nearby galaxy and seeing where it would show up on there. This is kind of more like a cartoon picture over here. This is what a spectrum of the gravitational wave background might look like, and these are possible single sources.
And the lines are
Oh, and
current sensitivity.
yeah, and no, yeah, well, I mean, those are very simple scalings that I think maybe Steve Taylor will go over on Thursday, just given how long you, so the question is, what sets these PTA sensitivity curves and what are these gold stars? The gold stars were single sources, and these sensitivity curves are kind of simple estimates giving some observation time and some limiting sensitivity. So they're just very simple. Oh, yeah. Well, you can, so the way it works with the pulsar timing arrays, this parallax measurement, is that you have Earth here and you have a pulsar very far away. And depending on the wavelength of your radiation, you can enter into what would be the Fresnel regime, which just means you're no longer in the plane wave limit. The curvature of your wave, gravitational wave fronts now matter. And so you can estimate when is that curvature detectable. And it turns out it depends on the wavelength of the radiation, the separation of your pulsar and Earth, and the distance to the source. So you can solve for a kind of maximum distance given the wavelength, and it can be of order out to a gigaparsec if you have really far away pulsars. So yeah. Exactly. That's a very good point. To do that, you have to know the distance of the pulsar within a gravitational wave wavelength, which can be extremely difficult. But in principle, in practice, it's still something that's being worked out. Yeah. Yeah, so the question was, if you can detect the same, say, black hole binary in LISA, and then it evolves, and we see it in LIGO, how can we know that those two events measured with different instruments at different times are from the same astrophysical source? Is that the question? I think that's a great question. I think one thing we'll be able to do with LISA is localize the source to some part of the sky, and then look for example, an electromagnetic counterpart when it emerges. That might not happen depending on the sources. But then you can also localize it with LIGO. The question is, how well can you localize it with LIGO and with LISA to determine that it's the same source? Because you do have temporal localization as well. When you see it in LISA, you know when it will merge to pretty good precision, which is probably exactly the strongest thing, because you have now said that because we saw this in LISA, this will merge within a second in the LIGO band, and the coincidence of another one happening is probably very low. So that's probably the best way that we'll know with the same masses. Well, maybe Johan will come up with some astrophysical formation channel where in the decihertz regime, the merger is caused by a third black hole coming in and changing mass. But if you want to, yeah. Very well, because there's many cycles, many cycles, whereas LIGO has tens or something like that. Yeah. Right. Great question.